multidimensional directed nanoscales assembly, Department of Material Science and Engineering, Korea Advanced Institute of Science and Technology, uh, Korea, Republic of Korea. So he has a vast experience in material science and solar cell, fuel cells. Uh, he has done a more elaborative research in all the technologies like in engineering and sciences, focusing on energy storage and conversion technologies, including supercapacitors, metal ion batteries, metal air batteries, water splitting, solar cells, and fuel cells. So, additionally, he inspired to pioneer the development of flexible biosensors for highly sensitive, selective, and reproductive and durable biomolecules detection from human body. So he has to he had contributed uh, very dedication and hard work to an innovative research or educational institutions to further advance his knowledge and skills in the uh, scientific domain. So he acted as a research. He did his PhD in the year of 2008 to 2013 from Anna University, Chennai, under the guidance of Dr. Pandurangan. He did his postdoctoral research in Brain Korean as a Brain Korean Fellow, Department of BAN Convergence Technology, and he did his research assistant professor. He joined as a research assistant professor in the year of 2015 to 20, uh, Department of Nano Convergence Engineering, uh, Republic of Korea. And then he promoted as a research professor uh, from February 2021 to till date, Department of Material Science and Engineering, Korea Advanced Institute of Science and Technology, Republic of Korea. So he has remarkable research and the teaching knowledges. His research, he has a lot of research funding. He had prestigious Korea Research Fellowship as basic science research program. These are all funding for under his research. There are two fundings he has available. He has made 1,060 1 lakh and 60,000 US dollar for basic science research program, and he has received 2 lakh and 40,000 US dollar for prestigious Korea Research Fellowship during the year of 2015 to 20, and he has almost 70 number of publications in various uh, uh, science cited indexed journals. So number of citations, he has 6,117 citation until now. So H index is 48. Uh, so he has published most of the research papers in some of the reputed journals like Advanced Materials, Advanced Engineering, Energy Materials, Applied Catalysis, Advanced Functional Materials, Nano Energy, Chemical Engineering Journal, uh, Journal of Material Chemistry, Biosensors and Bioelectronics, ACS Applied Materials and Interfaces. So he has numerous number of publications, about more than 70, and he has two patents under his name. While he is working in Korea, so he had two patents also. Uh, he had he has written more than two book chapters, and he conducted many conferences, international conferences, and he acted as an convener as well as organizing committee. So he had done almost 17 international uh, guest lecture from various conferences, international conferences. So convener for international conferences, he acted as a more than four international conferences. Acted as a convener. He has awarded many awards like Outstanding Research Award Korea. He uh, that he came as top two scientist worldwide, top 2% scientist worldwide, top 2% scientists worldwide from elsewhere Stanford University in the year of 2024, 23, 22, and 21. So 4 times he has come as a top 2% scientist worldwide in the year of 21, 22, 20, 23, 24. Uh, awarded Korea. He has awarded Korea Research Fellow in the year of 2015 to 2015, and Brain Korean Fellow in the year of 2014, and Senior Research Fellowship under UGC in India. That is April 2011 to 2013, and Senior Research Fellowship. He acted as a Senior Research Fellowship in the year of 2009 to 2010. So he has vast experience in solar cells and fuel energy production as well as energy conservation area. So he has vast research experience. He has the ability to handle all the equipments, almost all the equipments in this field: supercapacitor and lithium battery workstation, solar cell workstation, photocurrent voltage analyzer, autolobe workstation, galvanic galvanostatic charge discharge analyzer, electrochemical impedance analyzer, X-ray photoelectron spectroscopy, transmission electron spectroscopy, scanning electron microscopy, PET analyzer, FTIR, DRS, UV visible spectrometer. So these are all the instruments. He has well versed in these instruments. So with this, he had 20 pages of his resume. So due to sufficient of lack of time, so I have missed some of the wonderful work done by him. So with this, I conclude my introduction. So let me call him for delivering his lecture on biosensors materials. Thank you,
Thank
thank
you,
you, one and
Professor.
all. Uh, I
One
hand
minute,
over the
one
session
minute.
to Dr. Balamurugan, sir.
Thank you
Yes,
very
sir.
much. With this all qualities, you have a very good quality that when I approach you, you immediately accepted my invitation with your all
Thank you.
busy schedule. Thank you
Thank
very
you.
much.
Thank you.
Today, concluding day. So for the
Hmm.
concluding day, you are coming and giving your talk is very special for us. Thank you very
No.
much.
Thank you, Professor
Uh,
Ramasubramanian sir,
yes,
for
thank you.
giving the deep introduction about me.
Welcome, sir.
And thank you for Professor Adimulam sir giving the great opportunity to deliver the talk to the university, your colleges. So I am really happy to give or discuss the people with our country peoples, especially because we have conducted 3 conferences, international conferences, Korea, Indo-Korea conferences, VAT and the KAIST. Because the KAIST is one of the top university, because out of 300 university, this is the number 1 university in Korea. And the world ranking, below 20 ranking university, QS ranking, because this is the world top university. Another one thing, I'm happy to always serve as a are giving the lecture for our country peoples. I'm dedicated to give, because I love our country, because without our country, like our country is like our backbone. So I'm very happy to discuss about my research to our country peoples. I'm very really happy to give. Even this is not a busy schedule, because I am really happy to discuss all this. And still I'm like working as a student. I don't feel I'm like a professor. Another one good things, I am from today officially. Maybe luckily, I don't know. From today, I promoted as an associate professor, from assistant professor to associate professor. So this is my
Congrats,
first
sir.
introduction of associate professor. Getting associate professor from this university is not easy thing, because many panel members they have to select, because the KAIST very competitive university. And I'm very happy to give the first day associate professor with I'm giving the lecture for your colleges. I never forget this moment. So today I'm going to discuss about. So thank you everyone. So whoever participating in the conference. So really I'm happy to meet everyone. Yeah. So today I'm going to discuss about the single atom catalyst. Why we are going for single atom catalyst rather than metal nanoparticles or other type of materials. So what is the advantages overcome for other type of materials compared to the single atom? So today I'm going to discuss detail about the single atom catalyst. So what is the advantages towards sustainable energy storage and conversion technology? So the introduction sections including how the single atom is helpful for the next generation energy storage and conversion technology, and what are the techniques are helpful to enhance the performance of energy storage technology, and the experimental section including different type of material synthesis methodology, especially how the single atom is fabricated rather than nanoparticles, and resultant discussions which includes morphological investigation of the materials, structural investigations, and electrochemical performance in basic 3 electrode test and final device fabrication like battery technology, as well as so energy storage and conversion technology like water splitting technology. So if we have times, I can also discuss about the biosensor and biosensor related works. And finally, I'm going to summary and conclude the works. So in this area of single atom catalyst, so the single atom catalyst is used in different type of applications like water splitting, especially catalysis, hydrogen evolution, and oxygen evolution reaction and oxygen reduction reactions. And fuel cells and solar cell also, the people are using as a single atom as a catalyst. And the energy storage systems like capacitors and batteries. And finally, the single atom can detect the biomolecule from a body, especially the biosensors to detect the hydrogen peroxide, glucose. But what is the amount of hydrogen peroxide we can differentiate from the human body, normal human to the cancer affected baby. Then the single atom may be used in different type of application. I already explained about this. Usually the bulk nanoparticles have some surface free energy, but when bulk nanoparticles transform to the single atom nanomaterials, then the specific energy will be enhanced. And the people moving from the nano to sub-nano, and recently single atom is one of the challenging tasks to go for the high energy storage and conversion applications. Why the single atom is especially used for energy storage and conversion? Because it has high surface free energy and the activity is higher compared to the other bulk and nanoparticles. So therefore, people are making the single atom over the 2D materials. Why the people are choosing the 2D frameworks? The 2D frameworks have the higher surface area. Then the single atom may be homogeneously anchored over the 2D materials and helpful for the energy storage as well as energy conversion mechanism. So what is the advantages of the single atom towards the industrial aspects, especially R&D, research and development aspects? So how the single atom is better than the other previous catalyst what we are using as a industrial aspects like noble metals, especially noble metals are used as a industrial catalyst, hydrogen evolution, oxygen reduction reactions. So therefore the people are using as a water splitting application like a hydrogen productions. Therefore the people are using a hydrogen cars. Recently it already established in advanced country like Korea or Japan or USA, but still there is some lacking problem in India. But even though there is some city they're using hydrogen based cars, and the problem of noble metals, the high cost as well as the scarcity, therefore people moving to the noble to non-noble metals. When they have to go for noble to non-precious material, before that they go for noble metal mixed with non-noble metals, therefore to reduce the amount of noble metals. After that they make the core shell materials. What is the advantage of the core shell? Core shell may be prevent the active material from degradations, and non-precious materials especially giving the high performance, but even though still not certification for the noble metals amount of like a noble metals standard. Therefore the people going for the shape controlled material, and finally they go for single atom based catalyst. So when compared to the nanoparticles, the single atom giving a higher specific activity, because the single atom getting the higher specific activity based on the more active sites compared to the nanoparticles, because nanoparticles the outside surface area only active towards the electrochemical performance, the inside core material not involve the electrochemical reactions. Therefore mass activity is very low compared to the outside surface areas. Therefore when the single atom, each single atom involve the electrochemical energy storage and conversion applications. So the research strategy, how the people are making the single atom and how we are making the single atom towards the energy storage and conversion devices. First, I'm going to discuss about the energy conversion devices like metal air batteries. Metal air battery is totally different from metal ion battery, like a lithium ion battery, because metal air battery is based on the catalytic reactions of OER and ORR reactions. Both catalytic reactions involving in the air cathode, then it makes high energy and high power density rather than metal ion battery like a lithium ion battery. Therefore, people are moving metal air battery rather than metal ion battery. So in our case, we fabricated numerous number of the zip based organic frameworks like a MOF frameworks. So why we especially choose the MOF frameworks rather than other 2D material like a graphene? Because MOF based material has that the MOF-based material has a high surface area and high porosity compared to the 2D material like a graphene. Because when we are using the graphene-based material, the restacking effects will be happened. Therefore, the surface area will be reduced. After that, the reducing the surface area may be performance-wise, maybe reduction happens because the restacking material cannot able to involve the electrochemical performances. Therefore, the graphene-based material maybe reduce the electrochemical performance rather than the MOF-based materials. So when we are using the MOF-based material, we have to make some porosity like a PS. PS is a templating materials, polystyrene. After pyrolysis, the PS may be removed from the carbon networks and high rich component, enriched component of the carbon frameworks, and the single metal is easily attached to the nitrogen and easily bonded with the graphitic carbon networks. So we can use different type of the single atom materials like first row, second row, third row transition materials. So when compared to the first row material, then when we go for second row, third row, the cost wise is very high. But in the case of the second row, third row material, we can use for acidic media. But in the first row, we can use for basic media. When we are using for basic material catalyst like a basic electrolyte, we have to use the upper side first row transition material like a vanadium, iron, copper, molybdenum, iron, copper, nickel, or cobalt. So when we are going to, based on the application, we have to choose the first row, second row, third row materials. After that, we have to fabricate the materials. That fabricate material we have to confirm by the DFT calculation, density functional theory calculations. So from the density functional theory calculations, we can find the optimal catalyst. The optimal catalyst means the free energy close to zero is a better catalyst from the PDOS. And we also do the OR OER performance DFT calculations. So from the optimal catalyst, we have to fabricate the final device like a metal air battery. Our catalyst used as the air cathodes because the air cathodes may be doing both OR and OER in the same site. But in the commercial aspect, we have to use different type of catalyst for OR as well as OER catalyst. So after fabricating the material, we have to confirm the morphological investigation. You can see the same TEM and morphology STM images. From the SEM and the TEM analysis, we cannot able to predict the single atom catalyst because single atom catalyst only we can see below 2 nanometer scale bar in the scanning tuning electron microscopes. We cannot able to see by TEM. Only STM can detect the single atom. Another one great tool is the XF analysis. This XF analysis limited in country, even Korea, there is only one place available, XF, there is a Bohong. Then we cannot able to detect the XF analysis from overall many places. But the STM or TM available many institutes, but the STAX is one of the best techniques to study the local structures. The local structure means that single atom or metal nanoparticle formations we can differentiate easily. So when we see the single atom bonded nature also we can differentiate it because it bonded with the nitrogen or it bonded with the carbon or it bonded with the other sulfur or selenium or whatever the bonding nature also we can differentiate from this XF analysis. So the DFT calculations we also predicted the optimal catalyst because it close to the zero Fermi level, then it may be more active towards the OR or OER. And we also do the theoretical test before doing the device performances. We have to check the oxygen reduction performances by theoretical tested because the reference electrode usually we use based on the electrolyte. Acidic means we have to use a silver chloride, but basic means we have to use mercury HgO, and the counter electrode usually used for the carbon rod instead of platinum. Usually platinum may be corroded during the electrochemical performance, therefore we have to use carbon rods, and the working electrode should be our electrodes. Maybe it may be coated over the carbon paper or whatever the substrates, because like a current collectors. So such a single atom may be used in different type of the current applications like battery technology and educational purpose and storage mechanisms. Especially the battery technology, you already used in the aeroplanes or smart computers, as well as the some the house also they are using as a battery technology like a metal air battery, and they also use in different type of electronic gadgets. And the single atom catalyst used in different type of applications like engineering application, mechanical engineering, electrical, as well as different type of engineering applications, and energy storage device such as supercapacitors, metal ion battery, metal air batteries, and energy conversion device such as solar cells, fuel cell, water splitting, and finally the single atom based catalyst used for sensor and biosensor applications. When we go for energy storage technology, energy storage and conversion technology, we have to go for the highly flexible and variable technology rather than the liquid-based systems, because usually liquid-based energy storage devices may be critical to use for some cold country like USA, Canada, or Korea or Japan, because these countries going for minus 35 degree. When the temperature below 0 degree, then the electrolyte may be solidification. Therefore, the ion transportation may be big issue. Therefore, we have to prepare solid-based electrolytes rather than the liquid-based electrolytes. But in our country, we no need to worry about this kind of issue. Even though the liquid-based systems may be leakage, may be possibility. Therefore, people are going for solid-based electrolytes to fabricate the energy storage and conversion systems. And finally, such kind of solid-weight, thin electrolyte-based materials. And finally, we make the highly flexible energy storage technology compared to the other, when we are going for the highly wearable and flexible systems, we can use everywhere. We no need to worry about to bring we no need to waste our transportation mechanism, transport, and with the high prices. And metal air battery, you can see. So what is the mechanism of metal air battery? Usually in the air cathodes, they are doing OR and OER mechanisms. And metal, whatever metal we are using, then we call it lithium or zinc. Usually lithium, when we are using, we can call lithium air battery. When we use the zinc, we can call zinc air battery. There is many type of metal air battery is available, but why we choose zinc air battery rather than lithium air battery? Because lithium air battery, when we are using the lithium air battery, we have to use non-aqueous electrolytes. We cannot able to use aqueous electrolytes. But when we go for zinc air battery, we can use aqueous based electrolytes. Another one thing, you can see different type of energy storage systems like a cadmium battery, lead battery, and lithium ion battery. When compared to the other available battery, metal air battery giving the high specific energy and the specific power density. When compared to the zinc air battery, the lithium air battery getting the high theoretical specific energy density. But when we go for volumetric energy density point of view, because volumetric energy density is the commercial point, it's a commercial as practical points. So the zinc air battery giving the higher volumetric energy density compared to the specific energy. Another one good point, the safety is one of the issue, because when we go for the zinc air lithium air battery, we have to use for non-aqueous electrolytes. Then the non-aqueous electrolytes sometimes may be explosive happens. But in case of the aqueous based electrolytes, we no need to worry about the safety issue. Therefore, the people are using zinc air battery rather than the lithium air battery because of the safety issue. And another one thing, different type of aqueous based zinc air battery available. But why we are choosing zinc air? Because the zinc is low cost. Another one thing, highly reversible, because the rechargeable is very important rather than the only chargeable. Yes. Therefore, we choose the zinc air battery rather than iron or aluminum or magnesium air battery. So what is the problem of the zinc air battery or metal air battery? You can see when we use the metal air battery, the cost of the platinum based catalyst in the OR is very high. Another one thing, when we use the electrode material, the corrosive property happen, because the activated carbon supported the platinum may be highly corrosive and may be dissolved during the charge discharge process. Therefore, we are using the highly protective single atom based catalyst or highly make the new strategy making the highly durable catalyst like a core shell or other type of materials. So what is the current issues? You can see metal electrode as well as electrolytes. There is some issues. Usually there is a high cost, poor durability, and their war potential also very high. So when comparing to this current issue, we have to overcome with our new strategy. That new strategy maybe enhance the intrinsic activity, and maybe we can reduce the cost wise, and durability enhancement also happens. And both the 5-axis like OR and OER will be higher compared to the current issues technology. Another one thing, what is the current issue for metal electrodes like a lithium or zinc or whatever metal anode, and dendrite formation? Because when we are using the metal direct to the electrolyte contact, then the dendrite formation happens and the shape changes. Because of the dendrite, it may be highly corroded, then the shape will be changed, and passivation will be one of the issue. Because another one thing, this kind of issue may be overcome by our new strategy. We are making 3D based electrode materials to overcome this kind of issue. Another one thing, electrolytes, I told you the stability issue and the conductivity and the solubility issue also in the aqueous based electrolytes. Therefore, we are using some new strategy based non-aqueous based electrolyte, and maybe we make the solid based electrolytes. And from this new strategy, we enhance the performance and to increase the round trip efficiency and the Coulombic efficiency as well as cycling stability. So you can see this is the development technology. And finally, after fabricating the materials, we are doing the theoretical test performances, and we also do the DFT calculations to find the optimal catalyst. And after checking the optimal catalyst, we are going to the device called the metal layer battery. That device we cannot able to directly propose. That we have to compare with the commercial battery like lithium ion battery or supercapacitors. After comparing to the devices, we have to show this performance very high, and we can commercialize to the real world applications. So this is the new strategy. You can see metal layer battery. So this is the extension technology. What is the issue? So you can see before stability and after stability, maybe lose the metal active materials. And this is a new technology. We make the highly protective active materials by the 3D nano networks. And finally, we also overcome these drawbacks by scarcity, poor durability. By new strategy, we make the well-defined 3D nanostructures. And finally, we get the long cycle life and high energy and power density. And this is a new strategy, maybe helpful to get the next generation electric vehicles and mobile or computer devices. Maybe it may be promote to their real world applications. So these are the gadgets are already available energy storage, flexible energy storage systems. So we had communicated some paper, maybe published some papers like a molybdenum based single atom catalyst. So this is the design strategy. You can see we can take the graphene oxide based material and we do the co-precipitation by PDA, and finally make the molybdenum single atom. Because this molybdenum single atom with the core like a vanadium molybdenum nitride, because this strategy is the new strategy, because we use the coastal driven single atom. From the coastal driven single atoms, you can see different type of the kinetics issue may be overcome, and we enhance the energy density, power density, and the cell may be the energy shell, because the shell may be prevent the active material from the degradation, and the core shell confinement may be enhance the energy density and power density and cycling stability of the energy storage systems like a zinc air battery. So after fabricating the materials, we have to confirm by the morphology integration. You can see the same image. There is no, restructuring happens, because very thin nanoparticle as well as single atom may be homogeneously distributed over the networks of the graphene. And you can see there is no metal nanoparticle observed from the SAD patterns, because the single atom may be finely distributed over the networks, and the core shell may be around 2.4 nanometers core vanadium molybdenum nitride in the networks. And you can see this is the zoomed view of the core vanadium molybdenum and shell NC, because nitrogen over carbon, and there is numerous amount of molybdenum from the STM only. We can see the molybdenum single atom throughout the graphitic networks, and we also see the homogeneous distribution of molybdenum, oxygen, nitrogen, carbon. He further proved that the homogeneous distribution of the elements and the molybdenum is throughout the area, and the vanadium and nitrogen only present in the core. There is the vanadium not present in the single atom, only the molybdenum is present as a single atom, therefore it overthrows the area of the graphitic networks. So after confirmation, we have to do the structural investigation by XPS analysis. You can see different type of the nitrogen networks like nitrogen, like pridinic, pyrrolic, and graphitic nitrogens. And we also see many number of vanadium nitrogen bonding and the molybdenum nitrogen bondings. So from the studies, you can see the pyrrolic nitrogen is higher than pridinic as well as graphitics. So therefore, our material containing more number of pyrrolic nitrogens rather than pridinic as well as graphitic. And we also see the molybdenum with 2-3 different oxide shades, maybe del plus, 4 plus, and 6 plus oxide shades. And we also do the local structure by XAPS analysis. I told you the XAPS is one of the great tools to find the local structures. So this is the comparative material like oxygen, nitride, and carbide based material and metal foils. So when we see the R value, because the R value below 2, we can see metal bonded with the non-noble metals. Non-metal metallic systems like anions, metal with oxygen, metal with nitrogen, or metal with the carbon. And in case of this region, after 2 R value, metal bonding we can clearly see. From the studies, we can see this material containing metal nitrogen bonding or metal metallic bonding. So we also show the fitted diagrams. From the fitting curve, we can see 3 different type of nitrogen and 1 carbon, because the molybdenum bonded with the nitrogen as well as carbon bonded. So not only the nitrogen bonded. And vanadium, you can see the vanadium nitrogen bonding is very small, but vanadium bonded very high. So from the TEM analysis, you can see vanadium core shell, because the metal nanoparticle in the core shell, but there is no vanadium single atom. So this is WTEXF. You can see clearly comparing to the oxides, nitride, and carbide. In this case, the R value, because you can see this is R value, this is K value. So the R value below 2, we call that metal with the anion bonding, because molybdenum bonded with the nitrogen as well as carbon rather than molybdenum bonded. So after confirming the structural investigations, we do the ORR performance, oxygen reduction reactions. You can see when we do the oxygen reduction reactions, we have to see the onset potential, because towards the positive, the onset potential is very high compared to the commercial platinum carbon. We have to compare with the commercial platinum, but our optimal catalyst getting the higher onset potential and the higher half-wave potential, because half-wave means this and this, because in between the media, this is half-wave potential. So half-wave potential and onset potential is very important. Higher onset and half-wave potential, we can claim that the higher ORR performance compared to the other commercial as well as the other counterparts. And we also do the optimal catalyst with the different rotation speed of ORR. When increasing the scan speed rate, the current density drastically increased from the negative towards negative current density points. And the durability test before and after 5,000 cycles, they're almost maintained. There is not much loss happens. And you can see the durability compared to the platinum. The platinum maybe lost the relative current, but in our material maybe maintain the current almost 95%, more than 95% for 100 hours. And we also do the OER performance. You can see the OER we have to compare with the iridium oxides or ruthenium oxides. But in case of ORR, we have to compare with the platinum carbon. But in case of iridium OER, we have to compare with the iridium oxides. When we comparing to the other catalysts or even iridium oxides, our catalyst giving the lower OR potential, because this should be towards the lower regions, but here towards the higher region. Yes. So please don't misunderstood, but the lower OR potential is very important. So when getting the lower potential, maybe the better OER catalyst. So after that, the kinetics may be further proved by the TEFL plots. You can see the TEFL value, TEFL value very small, that called higher kinetics towards ORR as well as OER. When compared to the other catalyst, maybe lower TEFL value, because lower the value, maybe it is better for the ORR OER. And this is the real performance for ORR OER. And the close to ORR OER maybe, because the distance between this one very close, that may be called a better catalyst compared to the other catalyst. And the DFT calculation also further proved that when we comparing with the different active sites, we can observe that the molybdenum active sites, maybe molybdenum is the active site for ORR as well as OER, So you can see the mechanisms, how the oxygen is absorbed and how it may be released during the rate dynamic steps of the OR reactions. After confirming from the three electrode systems, we have fabricated the metal air battery. You can see the metal air battery, when we fabricate the commercial point, we have to mix 1:1 ratio of commercial platinum carbon iridium oxide. But in our catalyst, only our catalyst used as both the OR and OER catalyst, OER in the dual function, because that's why we call it bifunction activity. So the peak bound density almost 1.5 times higher than the commercial catalyst, and this also compared with the recently reported materials. It is higher peak bound density, and the practical applicability may be proved by the glowing series of LED, and the specific capacity very higher compared to the commercial catalyst. And we also do the durability. You maybe know the iron battery, we have to reversely come to the zero because the zero cell voltage. But in case of the air battery, we have to maintain both the positive as well as the upper side and lower sides, the potential, because the cell voltage. You can see this downside we call the OR. The upper side maybe we call the OER. So because we need to maintain the both, OER as well as OR, then only we can say this is the best catalyst when compared with the commercial, because commercial may be lost the cell voltage for both sides, OER as well as OR side, but our catalyst maintain more than 600 hours. And we also do the highly flexible systems like a 0 degree, 45, 90 or 180 degree minus 180. So this may be confirmed that both the upper side, because OER as well as OR may be maintained in the cell voltage, there is no loss happens. From this analysis, we confirm that our catalyst, our air cathode may be highly flexible in different bending angles, and we also do the different temperature tolerance ability, minus 20 degree to 80 degree. Then when temperature reduces, the cell voltage is maybe reduced, but not lost much when compared to the other commercial catalyst. I didn't show the commercial one here. So this is the summary and calculation, because whatever I discussed similar thing, because the peak bound density and peak power density, I told you the peak power density is very important compared to the other conventional material. Another one thing, the durability also get challenging, because the durability for 630 hours compared to the conventional catalyst like a commercial catalyst. From the studies, we conclude that our developed catalyst for both OER and OR are better performance compared to the other commercial catalysts as well as other counterparts. We also developed a different type of dual atom catalyst. Previously, I discussed was single atom catalyst like a molybdenum. So when we go for dual atom catalyst, I chose the iron fixed one. But when I choose the iron one, I choose the 2 first row transition metal, 2 second row transition metals, and 2 third row transition metals. Because I told you the second row and the third row transition materials more active in acidic media. But the first row transition metal only is perform high performance in basic media like KOH media or sodium hydroxide. So when I go for the universal pH like acidic as well as basic media, I have to go for the different row transition material. Therefore, I fixed iron. I varied different transition materials. When I varied the transition materials, I screening the material of dual atom like a rhodium iron is the one of the best catalyst. So after confirmation, I can see from the STM analysis, you can see that dark, because light more brighter is a bigger size of atom like a rhodium, and a smaller brighter is called iron. Everywhere you can see the dual atom is presented like iron rhodium. The distance between the iron rhodium around 0.257 nanometers. When post iron as well as rhodium, the oxygen directly absorbed the both sides because dual sides. Then during the OR OER, maybe it may be break during the OR performance, dual active sites may be effective for breaking as well as to getting the higher kinetics towards OER and OR applications. So for the basic, I told you that we want to make a porosity, therefore we make some PS molecules. You can see the homogeneous size of the PS molecules, and when drop over the carbon paper like a normal filter paper, you can see perfectly making the pattern. Yes, this PS may be helpful to make the high porosity in the graphitic carbon talks. So after confirmations, we do the X-ups analysis. I told you X-ups analysis, oxide shades when increasing this side, when going this side, the oxide shades will be increased. The metallic one, lower oxidations, around 0 oxidations. When going towards the positive, then we count higher oxide shades. The R value below 2 is called anion bonding, and after 2 is the metallic bonding. And we also do the iron as well as rhodium. From both structural investigation, we called that the iron rhodium acted as a single atom and bonded with 4 different nitrogen bonds. Therefore, we got the structures. Maybe I'll show you next. Next, I will show you the structure. And before that, I am going to discuss about the OR OER. So whatever I discussed previously. So higher onset and off-wave potential compared to the other dual atoms. So iron rhodium is only screened material and lower TEFL value, and you can see the durability test for 120 hours. Our catalyst may be highly durable, and the platinum carbide maybe lost the the potential relative current density. And we also do the alkaline media and acidic media. Alkaline media we use KOH media, and acidic media use sulfuric acid 0.5 molar. And when we use the acidic media also, we get the better performance for rhodium ion combination rather than the other combination of the dual atoms. We also do the OER performance with the lower OR potential and lower TEFL value and high durability and high performance for both the OER and the OR performance as a bifunctional activities. So after confirmations, we do the fabrication of the zinc air battery. We get the higher stability around 1600 hours, more than 1600 hours, and we also achieved a high peak power density. And this one may be 2.5 times higher peak power density even compared to the commercial catalyst. And the reversibility performance, because rate performance you can see when increasing the higher currents, then reversibility may be better for our commercial catalyst, but in case of the platinum maybe not better, platinum iridium. But you can see live video, live photo with the different bending angles, and we also do the different temperature tolerance ability. And this also may be similar. I know conclusion sections. Maybe I don't want to discuss more about the conclusion sections. I go to the next section because this is metal air battery. We published many papers about this area, and due to the time limited, I'm going to discuss about a few words. Next, we are going to discuss about the lithium sulfur battery. So why we are going for lithium sulfur battery rather than lithium? I previously discussed about lithium metal air battery. Yes, here we are going for lithium sulfur battery. Why we are going for lithium sulfur battery? Because lithium ion battery is still getting the lower energy density and the power density. Therefore, we are going for the cheaper one active material for sulfur, and we call it lithium sulfur battery. But there is one issue because lithium polysulfur formations. To avoid the polysulfur formation, we need to fabricate the catalyst-based material. That material getting the higher durability to avoid the polysulfur formation, because Li2S6 usually S8 converted into this is because discharging you can see S8 converted to Li2S8, S6, S2 and Li2S during discharging, and Li2S6 has to reversible. Suppose Li2S make a solid material, it's not reversible, then the battery will die. Yeah? Therefore, the synergetic kinetics to overcome by our newly developed materials, that material called cathode material. That cathode material maybe avoid the polysulfide shuttle effects. Then we can get the higher performance for lithium sulfur battery using low cost materials like a sulfur based catalyst. We fabricate the device. We fabricate the lithium sulfur battery by making the vanadium single atom with the rhenium sulfide anchored nitrogen doped graphene networks. You can see this is the strategy for synthesis methodology. So we fabricate the material by vanadium single atom into the rhenium sulfide networks, and it may be highly or homogeneously distributed over the graphitic carbon networks. And finally, we use it as a cathode because lithium sulfur cathodes, because After fabricating the material, we have to intercalate the sulfur because 80% of sulfur with our catalyst material, maybe 20%. And finally, we make the cathode and we make the device to get the higher energy density and power density. And after fabricating the material, we confirmed by the morphological investigation. You can see there is homogeneous distribution of the single atom with the metal sulfides. We cannot able to see the metal nanoparticle as there is no metal nanoparticle, even 2 nanometer scale bar. You can see there is no metal nanoparticle. We cannot able to see by single atom by TEM, but from the STM only we can see. And I show the homogeneous distribution of the elements. You can see perfect distribution of the rhenium sulfide and vanadium single atom. The vanadium single atom is a lower density compared to the rhenium and sulfur, because rhenium and sulfur homogeneously distributed over the graphite carbon networks. You can see the carbon, nitrogen also present because of the graphite carbon, and the rhenium sulfur homogeneously distributed, but vanadium acts as a single atom in case of our catalyst, our materials. And after confirming the material, we do the battery performances. You can see this is the oxidation as well as reduction. But when go for oxidations, the higher current density and the oxidation and reduction, because the reversibility is very important. Oxidation reduction very fast, then it is higher catalytic activity for lithium polysulfide conversion, because it may be prevent from the lithium polysulfide formations to getting the higher charging discharging ability. So when comparing to the vanadium rhenium sulfide nanoparticles, vanadium single atom giving the higher performance. You can see the blue one is the reduction and oxidations very close, yes, then the reversibility is very fast and higher current density in case of both anodic as well as cathodic peaks. And we also do the different scan rates. When the scan rate increases, the oxidation peak increasing towards the positive direction, and reduction peaks or cathodic peak increasing towards the negative directions. And we also do the impedance spectroscopy in the real and the imaginary parts. You can see I maybe forget to put minus name in the imaginary part. And this is the RS value, collision resistance, and this is the RCT. This RCT may be lower, and this one is the lower frequency, maybe ion transportations. The ion transportation better for our single atom rather than the other comparative catalyst. And the durability, you can see before second cycle and total cycles almost maintained both the oxidation and reduction peaks. From the studies, maybe we can conclude that our catalyst may be helpful to enhance the durability. And we also do the charge discharge process. You can see when compared to the other material, the vanadium material giving the highest specific capacity and the close oxidation reductions. And we also do the different coulombic value, because the different current density. When increases the current density, the specific capacity is slowly reduced, but the rate performance you can see compared to the other catalyst, the vanadium single atom based catalyst giving the higher rate performance and a higher durability and a higher coulombic efficiency. So from the studies, maybe we can say the device. We also make the pouch shell. After making the pouch shell, we do the durability and with the rate performance study. You can see different current density, and we get the higher coulombic efficiency. And we also do the before and after performances in the pouch shell. Maybe after 600 cycles, maybe we get the single peak redox peak, and the before one is 2. So based on the intercalation of some lithium, then we get the single RS and RCT values. So this is the conclusion. Maybe and you need to I think maybe from the studies we can conclude that our catalyst giving the higher catalytic activity for the lithium sulfur battery, and maybe the cycling stability very high, and the kinetics, maybe I told you the polysulfide conversions, maybe we need to reduce the polysulfide conversions, maybe enhancement of the kinetics towards the transportation of the lithium from our single atom catalyst. Maybe it's helpful for the next generation energy storage and conversion systems. So I'm going to discuss about the energy conversion systems like water splitting. You can see why we are going for water splittings by the the environmental techniques like a highly useful technique for the hydrogen productions. Usually different type of energy fuels is available: gasoline, diesel, natural gases. When compared to the other fuel sources, hydrogen giving the highest specific energy. And another one thing, the efficiency wise, compared to the other internal gases, the hydrogen fuels giving the higher efficiency around 60%, and the hydrogen fuels is more convenience and quiet, because the people always like quiet compared to the noise, the pollution. And another one thing, the clean environments. So in order to reduce the global warmings and to get the clean environments, we need to use for hydrogen gases. And I think already there is a lot of buses and many cars operated by hydrogen fuels in advanced country, even I think in the India also. So when I use the hydrogen, we no need to face many problem in the environmental issue. Another one thing, when we use the hydrogen fuels, maybe we can travel 1 kilometer by 1 rupees, because we can reduce the cost also. And maybe the hydrogen fuel source based traveling may be easier to quiet and clean. And already it is scalable, because the hydrogen fuel cell may be used in different transportation mechanism, transportation and industrial purposes. And you can see, so the current usage of the hydrogen fuels, and this is the future usage of the hydrogen fuel source. And so what is the techniques to produce the hydrogens? You can see the water splitting is one of the great techniques. You can see the ionic parts, oxygen evolution happens. The cathodic part, hydrogen evolution happens. When we are using the water molecules with the acidic or basic media, even we can use the seawater, because recently the people are using seawater to split the water molecule. From cathodic part, hydrogen evolution happen, and anodic part, oxygen evolution happens. So what the commercial company using hydrogen fuels, because the water splitting technology, platinum carbon as a cathodic material, and iridium oxide or ruthenium oxide is a anodic material. But when the platinum carbon, when we are using platinum carbon, the cost is very high. Even the catalytic activity very high, but the cost very high, and the natural scarcity and the durability is one of the great challenging. When we buy the commercial platinum carbon or iridium oxide or ruthenium oxides, we need to use some binders. When we use the binder, we have to use some acidic or basic media, even sea water, like a highly corrosive media. The polymer binder slowly degraded. So after few cycles, for example, we need to get the lower order potential for OER, and this is lower order potential of HER, hydrogen evolution. But you see, after few cycles, the potential increased drastically. But in case of the OER also, drastic increment happened after 22 cycles because of these polymer degradations. When we go for this precious material in the industrial aspects, we face this kind of problem for polymer degradations, because we need to fabricate the electrode over some current collectors using this kind of polymer. We cannot able to coat the platinum commercial catalyst or ruthenium directly to the substrate. This is the big issue. So in order to overcome this issue, we have developed a new strategy. You can see our strategy, we have to bring this potential to here. You can see our target should be here, because the higher water potential is not good for oxygen and hydrogen splitting mechanism. Therefore, we need to bring the potential lower water potential. Then when we get the lower potential, the splitting will be very easier. Then we can get the higher OER as well as hydrogen evolution performances. So in order to getting the higher performance, we need to fabricate or design the material. That material should be, designing material should be novel and highly active. And it should be reduce the OR potential for both OER as well as OR. So OER as well as HER performance. So we fabricate the strategy. You can see we took the transition metal chalcogenate substrate, and we use different type of the single atom catalyst. And previously I discussed about the graphitic network, but I am here using some transition metal chalcogenate like molybdenum sulfide, molybdenum selenide, or whatever transition chalcogenates. Why we use molybdenum or tungsten based materials compared to other chalcogenates? Because molybdenum, tungsten, or some tin based material giving the thinner one. When used as a thinner substrate, like a thinner networks, then the single atom easily anchor over the area. Another one thing, the thinner networks may be enhance the active size rather than the thicker one. Therefore, we use the transition chalcogenates, and finally we use some single atom to modification, and we use both the bifunctional activity for hydrogen evolution and oxygen evolution reactions. And from the strategy, we recently found this mechanism, but this is unpublished work. But this one, when we go for the high loading of single atom, there is one issue. When you going, because single atom should be bonded with some non-anionic bonding, like a sulfur or other bonding, not bonded with the metal bonding, like a metal clusters. Because when increasing the single atom, because each single atom getting the active sites, yes, we need to load the single atom with the higher loading, then only we can get the higher performance. Therefore, we are trying to the single atom loading higher, we get some problem by cluster formation. So to avoid the clusters, we get some new strategy for surface engineering mechanisms. From the surface engineering mechanisms, we go for more than 10% of the single atom loading. So we can load the single atom of ruthenium over the rhenium molybdenum sulfide, and after doing the phosphorization, then we get the single atom over the 2D material of rhenium molybdenum sulfide networks. You can see before, this is the cluster. You can see the metal nanoparticle cluster is observed, and this cluster may be clearly observed by the color mapping and HRTM analysis. So after the cluster, we got a successful transformed by the single atom. You can see there is no cluster observed. Yes, our strategy may be helpful to make the single atom with the high loading. I round up the single atom of ruthenium over the thin chalcogenate networks, and you can see the ruthenium single atom is throughout the area of the chalcogenates homogeneously distributed. It may be helpful. Each ruthenium is anchored the oxygen as well as hydrogen during the absorption mechanisms, and may be easily getting the hydrogen evolution and oxygen evolution by the active sites. It may be helpful for the higher active sites towards the both OER and HER performances. So from the studies, we also do the mechanisms. You can see when we see this value, because this energy value lower is oxygen of 0. You can see the ruthenium foil means ruthenium bonded, because oxygen 0, ruthenium 0. But when go for the the ruthenium single atom, even compared to the cluster, the ruthenium single atom may be around 1.5 or 2 oxygen shades. But when go for 2+, maybe this is 2, but maybe this between the 1 and 2, then we called maybe 1.5 oxygen shades. So from these studies, we conclude that the ruthenium as presented as single atom, and we also see ruthenium, because the cluster, few amount of ruthenium sulfur and remaining ruthenium bonding, because lithium bonded with the bonding means called a cluster. But when transformed to the single atom, there is no peak observed after 2 R values. Then we confirm that our material is 100% of transformation from this cluster to single atom. So this also additional confirmation for the single atom with the cluster. You can see the R value below after 2, because more than 2, but this is below 2. From this study, finally confirmed that our single atom is 100%, but in case of the foil containing more ruthenium bondings. But here only ruthenium bonded with some non-anionic bonding like sulfur and phosphide. And you can also see the ruthenium oxides. You can see ruthenium oxygen bond and ruthenium metal bonding also presented. And this is the cluster. Cluster majority of metal may be present in the ruthenium bonding, and a few ruthenium sulfur bonding. And we also do the express analysis. From the express analysis, we also see differentiate of the oxygen shades. You see higher binding shades, more oxygen shades. Lower binding shades is lower oxygen shades, maybe around 1 or 0. Yes. Then the cluster may be lower oxygen shades, but in case of the single atom, maybe higher binding shades. And we also do the other elements like rhenium, molybdenum, sulfur, and phosphorus. So before phosphorylation and after phosphorylation. And after confirming this material, we do the HER and OER performance. We can see the blue one is cluster, and the red one is the single atom transformations. After single atom transformation, the over potential drastically reduced, and the durability may be 400 hours may be highly stable in the potential maintaining for 400 hours. But in case of the OER, lower over potential and compared to the cluster and the commercial catalyst, and the high durability for 400 hours, even HER and OER performance. And finally, we make the water splitting performance. Water splitting, compared to the commercial catalyst like platinum and iridium, and ruthenium getting the 1.43 voltage. But this case of the platinum maybe around 1.53 voltages. But this work all done in the acidic media, not in the basic media. So, and the durability for 300 hours, almost 300 hours, more stable, without any loss, the potential maintained at the longer time period. From the studies, maybe we conclude that this single atom transformation may be helpful to enhance the electrocatalytic activity towards OER and HER. And next studies, maybe we also do some more work based on these water splitting applications. You can see here selenium is the active sites, and you can see the copper and tungsten selenide, because when you enhance the copper loading, the performance will be enhanced. Another one thing, there is no report such selenium active sites. Usually metal is active site for OER and HER, but in our case we predicted the selenium is active sites, anionic active sites. Therefore we plan to go for this publication, and this one confirmed by the structural investigations by XPS and XAPS analysis, and we also do the performance by OER, HER performance, and the TEFL value and the durability test we compare with the commercial catalyst also, and finally we make the devices like a water splitting, and we get the performance. Maybe this is the DFT calculations. You can see that from the DFT calculation, the optimal catalyst for higher copper loading compared to the other ratio of copper tungsten. But this one, the selenium is active sites. It close to zero because the free energy close to zero easily split the hydrogen compared to the other active materials. And we also tested different pH value. When increasing the pH, maybe the activity may be reduced, but lowering the pH may be better activity around the 8 pH. In case of the OER, you can see OER mechanism usually different type of mechanism, maybe OOH mechanism. Yes, maybe this is the read-in steps. When compared to the other top media, because like other active sites, selenium is close to zero Fermi levels and lower the value compared to the other active sites. Therefore, we claim that the selenium active sites, the optimal catalyst of 0.75, 0.25 selenide is the better catalyst. So we also do the mechanisms by DFT calculations. You can see how oxygen absorbed and how released during the oxygen evolution reactions. Finally, the device, we do the device. You can see the lower onset potential, cell potential, and even higher current, there is lower potential. And we also comparing with the commercial catalyst, and we also do the theoretical and experimental value, hydrogen and oxygen evolution reaction. Oxygen evolution, we calculated even 80, 160, 240, 320 seconds. And we do the reversibility test. Usually reversibility means the down one is HER and the upper one is the OER. But when go for reversibility, the current density should be maintained. But in case of the platinum, maybe loss of current density. The black one, you can see the loss, but in our case, may be maintained. And we also do the commercial aspects. We do the full cell devices like AEM, because anion exchange membrane water electrolysis. When go for acidic media, we have to use PEM, proton exchange. But here anion exchange water electrolysis, and we do the stability test for 200 and even 500 degree, almost maintained. But in case of the 600, maybe little oxidation happens, but not much. So therefore, we claim that this catalyst is one of the best catalyst for both OER and HER. So even we have to prove by the crystalline nature after durability test. You can see the crystal may be maintained, crystal structure maintained. TM and STM analysis, FFT clearly says that the crystal pattern maintained and the selenium almost retained. There is not much loss during the oxygen evolution and hydrogen evolution in the bifurcation activity of OER and HER. You see the practical applicability. So when doing, when connecting our device, because the air battery with our device, you can see both the OER and the HER, how it will release. Because I connected here, now I connected. You can see one electrode liberating hydrogen, another one electrode liberating oxygens. And from the studies, maybe we can say that the lower cell voltage compared to the commercial catalyst of 1.53, but our catalyst may be 1.49. But we make the anion exchange bottle exchange like a commercial point, and we also tested with the different high current density. And from the studies, maybe we can getting the high sustainable hydrogen productions. So we thought that this catalyst may be commercially easily because of the high ion expressions, lower over potential, and high durability. And we also make a many number of catalysts for hydrogen ablation and oxygen ablations. Maybe I don't want to discuss here. Maybe more number of works. So next I'm going for the capacitors. You can see so many number of electronic vehicles and electronic Georges. Nowadays people are using capacitor based or battery based materials. So this is energy storage mechanisms. You can see the difference between the capacitors and battery. So usually battery we have to call anode and cathodes, but in case of capacitor we have to call the negative electrode and positive electrodes. But we no need to confuse anode cathode in capacitors. In case of the commercial capacitors, the activated carbon we have to use negative electrodes, but in case of the positive electrode we have to use metal oxides. But in case of the battery, usually the anode material, graphite based material people are using, or lithium based material, and cathode we usually use the iron, cobalt, or whatever transition metal, but intercalation of the lithium, because lithium intercalated cathode material we have to use. During the charge discharge, the yttrium should be intercalate and de-intercalates maybe during the reaction will happen through the electrolytes. And this is, you can see the cathode lithium ion battery, this is the anodes. And capacitors usually getting the higher power density, but the energy density is one of the big issue. But in case of the battery, we can get the higher energy density, but the power density is a big issue. Here, the capacitors power density high, but energy density issue. But the battery higher energy density, but power density is one of the big issue. Therefore, people are using some battery type material for capacitors to make the hybrid capacitors to getting the higher energy density, power density towards the commercial aspects. And you can see the flexible energy storage device, what I told you, the flexible energy storage devices we have to use for the next generation energy storage mechanisms. we can fabricate the flexible energy storage by gel alkydes, and this is our strategy how we make the highly flexible energy storage devices. And the flexible energy storage devices used in different type of electronic chargers and self-charging clothes, and already commercially the Samsung and the LG commercially getting some ion and different type of automobiles. It's also used highly flexible energy storage systems. And how the connected devices like solar cells, we are using solar cells to storing, because solar cell usually getting the energy and to transfer to our battery to store, how it will happen, because interconnected systems. I'm going to discuss how we explore the materials one by one. We started our supercapacitors work because after I'm joining as foreign country as first postdoc, and after that I transferred to the research professor. So during the period I started maybe 2016, we started the material capacity material, powder based materials. First we choose the metal oxide, metal sulfide, metal nitride with the graphitic carbon networks like a graphene oxide or some other different type of graphene based networks. When we use this kind of materials, we have to use some current collectors. That current collector usually we use nickel foams. Why we choose nickel foam? First of all, because nickel foam is the highly porous networks, may easily helpful to adapt our materials and load the higher material, and maybe the electrode easily penetrate into the active material to getting the higher storage performance. Yes, therefore we use nickel foam. You see, first we make the hybrid material with the graphene networks, and first we make the only single positive material or negative materials, and finally after we see some problem of negative material like activated carbon durability issue, therefore we fabricate both positive and negative material to fabricate the full devices. Even still 2019 or 2018 or 16, we do many type of the graphene hybrid materials, but powder type materials. After we fabricating the problem of the device after 10,000 cycles, then we moved from the binder with the binder free materials. You can see when we go for binder free materials, we choose the nickel foam as a substrate. Before nickel foam, we need to grow the nickel foam over the active materials. We have to wash the nickel foam clearly, because nickel foam usually getting the nickel oxide layer. So in order to remove the oxide layer, we need to use some hydrochloric acid treatment and ethanol and water treatments. And finally, we use a nickel foam as a current collectors to grow the active material like a wire type, sheet type material. So after wire type or sheet type material in the vertical directions, the electron easily penetration, yes, then the more active sites will be happen. Then one good thing here, we avoid the binders. Then we get the higher performance for the energy storage like a supercapacitors. You can see first we make the coastal material for metal oxides, and we moved metal oxide to metal sulfide. And after metal sulfides, we moved to metal selenide based materials. So what is the difference between metal sulfide and metal selenide? Metal sulfide means very smoother area, but metal selenide, because selenium is bigger size, then porosity will be enhanced. From the porosity, maybe we can get the higher energy storage performance compared to the sulfide based material. Therefore, from sulfide to selenide, we have moved. So you can see even metal sulfide based material, we get the higher performance, even rod type or sheet like morphology, because of the hierarchical structure vertical grown over the nickel foam. Even though there is some big issue when we go for the practical aspects. Nickel foam, after growing nickel foam, we cannot be able to bend many times. Few times we can bend, it will break because this is metallic substrates. Therefore, we are directly go from the nickel foam substrates to the carbon cloth. You can see carbon cloth. After the carbon cloth, we are using the both positive material and negative material. After fabricating the positive and negative material, we studied by morphological investigation and 3 test performance. And finally, we make the device to achieve the high energy density or power density and high durability, especially long-term cycle stability. So based on the metal sulfide and metal sulfide selenide based material, we grow the carbon cloth. First, we used powder based material, and we moved even powder based material means a hybrid, graphene hybrid material, and we moved to nickel foam substrate and carbon cloth substrates. And material also we transformed from metal oxide, sulfide, selenide, and phosphate selenide based material. This is our transformation of the material, strategy. You can see we make some new strategy compared to the conventional strategy, like a coastal strategy. From the coastal strategy, we make the metal nitrate. Usually metal nitrate formations, we need to use ammonia gas. Even ammonia gas, we cannot be able to use many countries because limited ammonia gas, it may be polluted environments. In our strategy, we use the metal nitrate and the coastal. But in case of the conventional methodology, different kinds of metal nanoparticle only absorb on the graphitic networks. But in our method here, we make the core shell simultaneously, and we make the oxide to nitrate transformations because we use a cyanamide based material. You can see clearly metal nitrate nanoparticles encapsulated by graphitic carbon networks by 2 layer. And we studied the optimal, the potential by different potential, maybe we varied the potential from 0.4 to 1.6. Even we go for beyond 1.6, then some oxygen evolution happened. Therefore, we are stopped up to 1.6 because aqueous media, and we get different scanted effects and charge discharging. And we also comparing negative material for activated carbon, because when you go for negative material, when the high current density, maybe the rate performance will be low. But in case of the both positive and the negative material, in our material getting the high rate performance, and the practical applicability by glowing LED, and the durability for 24 hours. And we also do the practical applicability by different flexible energy storage systems. And we also do some highly wearable devices in our laboratory. We take the cloth and we put some conducting layer, and after that active material we grow, and we make the device like supercapacitors to get the higher energy storage performances. And this is maybe also we do both the active materials. So one interesting thing is when we grow the iron based sulfide, you can see there is no strict structural morphology. When nickel be mixed with iron, you can see the morphology transformations from the particles to the sheet-like morphology because of hierarchical sheet-like morphology. When we use the particles, maybe in the carbon cloth, E fiber, it may be dissolved during the charge discharge. But in this network, vertical grown, the hierarchical sheet-like morphology easily helps us to penetrate the electrolytes and enhance the performance. So after confirmation of the morphological and structural investigations, we do the device and getting the higher energy storage, energy density and power density. And we also do the high durability, and we also test out different current density with the charge discharge, as well as the cycling voltammeter study with the different scan rate effects and rate performance with the different current density. So this is the final discussion about the energy storage devices, because usually the supercapacitors we can use for the higher energy storage performances and getting the higher energy density and power density, and finally we make the long cycling stability and glowing LED, and will be helpful to tell the practical applicability. And we also do the zinc ion battery, maybe zinc ion battery, and this is also similar to the supercapacitors, because when go for supercapacitor we can go for 1.6 voltage. When go for zinc based negative electrodes, we can go for around 2 voltages. When voltage increases, is directly proportional to the energy density. So you can see why we are going for zinc based ion battery compared to lithium ion battery, because lithium battery easily explosive and high cost, because lithium scarcity is one of the issue. And zinc is acoustic based battery, low cost and highly reversible and long term stability, and material also very capacitive, highly capacitive material, and maybe high redox components like a transition metal chalcogenides. And we fabricate the materials, and maybe this kind of materials, maybe we do some morphological investigations. We also do the negative material by zinc. We directly vertically grow the zinc nanorods, and we use as a negative material for the zinc ion battery, and we get the performance. Maybe you can see. So we get the performance. I told you the battery capacitance we can go on up to 1.6, but here we can go up to 2.2 in the CV, almost 2 voltage. Yes, but there is very trace amount of the IR drops, and the higher performance in the this is aqueous media, and this is solid media, solid battery. This is aqueous battery, and solid battery is almost similar. And you can see we comparing with the liquid based battery and the solid based battery, and the high rate performance is also achieved, and high energy density, power density, and we compare to the other commercial catalysts, so the other commercial energy storage systems. And the flexible systems, you can see different bending and twisting. You can see the bending and twisting mode in the photograph. And we also tested, you can see when twisting with the and bending with the different angles, and almost the charge discharging, there is not much loss. And the quasi solid state may be getting the higher RCT compared to the liquid based battery, because quasi solid state usually ion transportation is not easier. Yes, because solid media ion is not very fast transformation, but the liquid media very fast transformation. And this is the conclusion of the the work, and I'm going to discuss about our research team. You can see the Professor Sang-Ho Kim. He is one of the leading professor in Korea, and he is the editor for energy storage material, because the first impact factor maybe 17, and now maybe 20 to 21 impact factor, I think around 21 impact factor in the Elsewhere journal. He is the top 20 leading scientists in the world, and he is pioneer for single crystal graphene. And I am working as a research professor in this team, and there is many postdocs and administrative staffs, many number of students, and usually this is because this is the Korea has 300 university. Out of 300 university, our KAIST is number 1, and difficult to enter this KAIST. Therefore, only the Korean students are studying, well skilled, highly skilled students, and these are the master degree students also study here. And you can see our teams. Here you can see our teams. Because this is the Professor Sang-Ho Kim and me, and there is some research professor and postdoc and students here. And we have different teams like graphene teams, BCP, polymer based teams, and catalyst teams, and we also working different type of research area. And you can see the KAIST. I told you previously, the KAIST is the number 1 institute in Korea, because the small country, but 300 university overall Korea. Out of 300, that is number 1. And the Asian place is maybe 4th or 5th place, I think. The Asian country is the 5th QS ranking, and world ranking is below 20 for last 8 years continuously, because this is Engineering Technology Institute. And this is the campus. You can see the different view of campus, and you can see the video here.
Determination. We are determined to pursue the highest goals. The term and
When the
report
video is not
global
running,
emergence of
not
KAIST 30 years ago, even before KAIST was created.
when the video is not visible.
A firm belief and commitment to developing ideas contributed to today's KAIST.
Excuse me, sir. I can't see the video.
Oh, really? Okay. Okay, just 1 minute, ma'am. No, ma'am.
Yeah.
Now can see?
Now it's
Yeah,
okay.
yeah, we can see, sir. Thank you.
Okay. Can zoom or it's okay, ma'am?
Determination.
Okay, it's okay.
Yeah, it's okay now, sir.
Pursue
Okay.
the highest goals. The term and report predicted the global emergence of KAIST 30 years ago, even before KAIST was created. A firm belief and commitment to developing ideas contributed to today's KAIST. We have worked hard to address the problems faced by Korea. The first Korean satellites that were made by KAIST are now known through the world. The first humanoid robot in Korea, Hugo, emerged as top global technology. Now, based on these achievements, we are moving forward toward new challenges to make the world.
Thank you. Thank you.
Thank you very much.